don't know why the overhead's not. What? Oh, there it goes. Okay, great. So I'm showing the syllabus schedule one more time. The last time I missed class was actually unscheduled. I had a trip I didn't plan. This one's been on there since the beginning of the semester. So next week I'll be gone. However, I am going to we're still going to assign kind of like a capstone lab. And this lab, unlike most of the others, some of them have actually been starting to kind of say, well, remember when you did this? Do it again. And the final lab here actually has you start a project or complete a project that is only described. Okay, and so hopefully I'll talk about that a little bit. But just like any other lab, we'll still have 2 weeks to complete it. So GHY will be in here, and hopefully Corey will be down there to help you a little bit with next week's lab. Although I won't be here, there's like a final lab that basically just has a paragraph about what I want you to do, and then has you attempt to complete it. I realize there'll be some help from either me or from GHY to complete that as well, and that's fine. Ask questions. So that's next week's lab. This week's lab is the final lab that has more of a cookbook style. However, it will prepare you for next week's lab because it's really the same content. The lab's the same content. It's just we're trying to build up to this in this course to be able to do some analysis on your own. And it's kind of like a good jumping off point for this course because the next course, there's actually 2 courses. There's 417 and there's 418 that continue this course. And 418 basically builds on a raster GIS modeling and talks more about hydrologic analysis, talks more about spatial temporal modeling, which we kind of bring up today, but we don't actually do it in this course. Whereas 417 does vector GIS, like network modeling and things like that, spatial interpolation. Now, those courses, although they're numbered 417 and 418, there's no one's not a prerequisite of each other. You just have to, everything has to have a number. So 417 and 418 are both the only prerequisite is this course in college algebra. So anyway, that's why we're progressing in this fashion. And then this week, it says cartographic modeling 2 continues. There's no new lab assigned on the last day of class. So really, this is the second to the last lecture and the second to the last lab assigned today. You'll get the final lab next week, and you'll get the final lecture on May 3rd. We're getting close to the end of the semester. That's always good news. So that's I'll been up in my thing for a little while. You can tell I don't reboot my computer very often. Next week Easter, or you already had Easter. That was from the 315 course. They wanted me to take a note. Okay, so today I've uploaded the lecture, so you can see it here. It doesn't have too many slides, but I'm not sure exactly how long it'll take us to get through the slides. I will try to upload the lab for next week, because I already have it mostly done. Just trying to adjust some of the data. I'll try to have that up in the next couple of days, so that you can start working on it. And if you are working on it and you feel comfortable and you complete it, then you have to come in and talk to GHY. If you need help, then come in next week during normal class period. She probably won't be here until, I'll tell her to be here a little bit earlier. I'll go find out when she can get here by before today's over. Okay, I know Corey usually gets there before lab starts. So that's the lecture for today. All right, like I said, this is kind of like where we've been going the whole semester, is to start learning about doing this kind of stuff, analysis using GIS. Go ahead. I don't know why that takes a few seconds. All right, and let's talk about spatial modeling. So what are we talking about here? Well, the term model in general means a description of reality. And in fact, we've used the term before. We've used the term, even in this class, we've talked about data models. A data model is a way to simplify reality and to store attributes and information about reality into the computer. So we talked about the vector data model and the raster data model. Those are two different ways. But those data models are similar to like scale models, but they're virtual. So a scale model would be like, you know, when I was a kid, I built a few little model rockets, shot up, or I don't know, maybe you did something similar with, or had something similar, models of larger things. We talk about model trains, model boats, whatever. Those are scale models. And a raster or vector GIS data model is actually very similar to that, but it's just, instead of being shrunk down, it's stored in a computer. And that's how it's a model, this description of reality. And we're going to distinguish that, separate that from what we're talking about today. What we're going to talk about today are basically process models or decision-making models that attempt to actually model something that happens in nature so that we can study it and we can make a decision about it. So those type of models, they can be either dynamic or static. In other words, they can be changing, or they can always produce the same answer. And so we can have dynamic spatial models and static spatial models. Today we're mostly going to talk about static spatial models. In other words, if we're trying to, a lot of these turn into like capability, suitability exercises. Which areas would be the best to place a new shopping center? Or which areas are the best habitats to preserve, or which are the best habitats for a certain species that we're looking for? Those are static spatial models because typically when we insert the data and do the GIS analysis, we get an answer. And if we repeated the same process, we get the same answer. Dynamic spatial model, the data itself has to change each time. So one way it could change is through modeling something over time, or we could introduce some randomness, because in real life there are random events that happen. For example, we could try to model the spread of a fire. And what we could do is say that the fire will spread based on probabilities. It will probably go in the direction of the wind. It will probably go in the direction of the highest fuel load. But there's some things about this complicated process that we're just going to leave to a random element. And we could model how that fire spreads. We could do that in a GIS system, but it would be a dynamic model. Oh, down there they can't see the screen? Y'all can't see the screen down there? No. Oh, you can't see the, they actually have another, this on another, they have two screens too, so they see, you're right, but they can't see me. So oftentimes, geographic information scientists will divide spatial models into 3 different classes. So we're going to focus on cartographic models today. Okay, cartographic models. But we also have spatial temporal models, which are basically building off of this concept of cartographic models, but the inputs will change with each iteration. So we can model the growth or the spread of something. And that's a topic that we actually discuss in pretty good detail in 418. All right? And network models is a topic that we discussed pretty well in 417. So we're going to talk about cartographic models today. Actually, before I leave that slide, let's talk a little bit about spatial temporal models. Okay? So they're dynamic in that they change. So once we talk more about cartographic modeling, this might make sense. But let's say that we were modeling rainfall runoff. Rainfall always the same? Maybe like in Seattle or something, but not around here. Sometimes it's dry and sometimes it rains, right? In California, you could say it's always the same too, where I grew up, because it rarely rains. It does rain every once in a while, but almost never. So anyway, things like rainfall would change. So if you're going to model that in a GIS system, and you wanted to model it on a daily basis or a monthly basis, you have to be changing those inputs. So time passes inside the model by the input data changing each time. All right. It's having a hard time deciding which of those 2 slides should be first, because this one is describing cartographic models. Right? Temporal models will build on that. So cartographic modeling is the application of a lot of spatial operations together. When we start connecting these spatial operations that we've talked about over the last few weeks, such as buffers, interpolation, which we actually didn't discuss today in this class, it's something we discussed in 418, reclassification, and overlay in order to solve problems. So we combine them all up to solve problems. I'm going to show a few examples today. Like I said, lots of times these get called suitability analysis. You did one of these in the earlier labs, but maybe we didn't present it as a cartographic model at that time. And oftentimes, we get combinations of various layers. We call that combination, we put that into a function and get a new layer. So every time we do something like this, we have one or more layers in a function that produce a new layer. Typically, they don't change unless it is a spatial temporal model. All right. So these can get fairly complex, these cartographic models. And we're talking about these functions and operations. Actually, I'm going to go ahead and peek the next slide here for a second. Oftentimes, we draw these processes as flowcharts. So this is a flowchart. See these arrows are flowing. So we start out with layers, and we have the operations. In this flowchart, we're showing operations as circles, layers as squares, or data as squares. I don't think that matters that much what shape you use for different things, as long as you're consistent. So here we have squares representing the data layers, I guess the rectangles, and then this is an operation, this is a buffer. So we start with lakes, we buffer the lakes, we get the areas close to lakes. Start with roads, buffer the roads, we get the areas next to roads. Start with hydric status, we reclassify it, and we get just the wetlands of the hydric status. And then we can combine our layers through overlay operations and come up with a suitability ranking Here we might have been trying to find out a good place for a particular habitat. All right, so going back here, distribution of suitable habitats is one thing, but these are some other things that we can do cartographic modeling with to answer. Okay? Migration routes, water distribution systems, species invasions, mill site selection, harvest scheduling, pollution response planning, any type of site selection, whether it's socioeconomic or biological, any type of those. All right, so we often represent these things graphically with flowcharts. Here's just another example. Oftentimes, when we're trying to come up with a suitability ranking or a capability of a land to support a particular activity, and it's a combination of factors, okay? In other words, it's decided by, in this case, criteria layer A and criteria layer B. We could say that the overall suitability is a combination of layer A and layer B. And sometimes we might want to say, well, layer A is more important for this particular thing. Okay? If we're trying to site a new grocery store, it might be more important to be closer to a particular class, like age class of people. Who knows? Like or it might be more important to be next to how far away you are from an existing grocery store. Things like that. Okay? Whatever these different criteria are, they could be weighted, and the weights would be multiplied, and then you could add them up to get a suitability. So suitability could be simply additive, or it could be a weighted combination in order to achieve a suitability for a particular activity. Rankings can be discrete. In other words, we could say this 1, 2, like on a scale of 1 to 10 or 1 to 5, or rankings could be continuous, meaning that there could be all sorts of different possible values. So here's a source layer soil type. We could have a rule that says if production is less than 66, the rank value is 0, else the rank value is 1. In other words, these areas, the 0 areas, were totally unsuitable, and the 1 areas were totally suitable. Okay? The 1 areas were totally suitable, 0 areas are totally unsuitable. Or it could be continuous, meaning that the rank was based on the production values and scaled. So that might be more applicable like in a situation where we're building a new road. And building a road on a flat surface has some cost associated with it. Okay, let's just say $10 per foot. I'm just making that up. But as the slope increased, the cost to build the road increased. And so there could be some sort of multiplicative factor after that. So if the slope was 0, so basically you could say the cost was 10 plus whatever the cost was for the slope. As the slope increased, it cost more and more. So one of the big tasks, or one of the big things that's often left to determine is this basis for your rankings. How do you decide what's important, and then how do you actually put that into the GIS system? So it's often based on science, but you may not be the scientist for that job. You may have to gather a collection of scientists. So here's an example of weights based on distance to roads. So start with a roads layer, and then we could run a proximity analysis and get a distance to roads layer and come up with a road suitability score once we had a suitability relationship. So here's distance to road, and here's the suitability ranking. So in this case, there's kind of a sweet spot right around 1200. That area is the most suitable. And it falls away if you get too far from a road, and it falls away if you get too close to a road. This could be a situation like, I don't know, maybe even something as simple as building a picnic area. Okay? Finding a good place for a picnic area. You don't want to be like right next to a road in order to build a picnic area, because then you get the cars driving by. However, it may be that you don't want to be too far away from a road, because then it would cost associated with building a new picnic area would be too much for the local government to bear. So if you're too far away, building a new road out to the picnic area wouldn't be as useful. Anyway, so they don't have to be strictly linear is the point there. So here's an example, slope suitability ranking. I already kind of talked about this. But you have an elevation layer, and you have your slope layer. Then your suitability, which could be cost. In my previous example was cost. Your suitability. Then this is basically just a function, a linear function. As slope increases, your suitability decreases. So there's the suitability score. And both of these cases were continuous data, and we're ending up using a raster data model at the end. Okay. So we had a vector data model to begin with here, but we converted it to a distance layer. So it's a raster data model. And at the end, we probably use a raster calculator function to create this. Okay. But and in this one, we started with an elevation layer and created slope, and then created a slope suitability layer. So in both of those cases, we did a raster, our answer was in raster. Oftentimes, when you go about to do cartographic modeling, if your answer is going to be like a continuous value, oftentimes it's best to use the raster data model. If your output's going to be discrete, in other words, like yes or no, or maybe one of 5 or 6, 7, 8, 9 classes, then it would be best to use the vector data model. So here, we could have said, okay, well, any area between 750 and 1,750, all of those areas are good to build a new picnic area. In that case, we could have just buffered that out about 750 meters. So we buffered that out about 750 meters, and our road suitability score would be 1 in those areas and 0 in the other. So sometimes our answer may be to use the raster data model, sometimes using the vector data model. All right, but still, we're getting back to this question. How do we combine the rankings from various layers? The relative weights among your input layers will substantially affect the relative suitabilities you predict, obviously. If I chose a different weight, then it's going to weight that differently and produce a different result. How can I decide how to determine these weights? Well, one way to do it is to just leave them unscaled. Okay, don't use weights. So that has the effect of assigning them all the same weight, or a weight of 1. You notice the math here says you multiply the value by a weight, add it to the next pair where the weight is multiplied by the value. So that's unscaled. A common scale, which would mean some pre-existing scale that was out there for that particular application. This is one that I actually do a lot in the work that I do. So a lot of times I use GIS to help people to either establish protected areas or to rank areas in terms of their importance for protection. And so in order to do that, what we often do is call a meeting of experts in this particular area that we're working in. So if it's a particular island in the Caribbean, we get together the folks that use the fisheries and the folks that use the other natural resources. And we get them to kind of determine or to come up with weights. And they say, well, this particular element of the environmental area is the most important. And relatively speaking, this is the least important. And so we can come up with a way to weight these things based on those expert opinions. Or taking it from the other direction, what often happens is that we look for activities that could threaten threats to the protected areas, to come up with a consensus on which things are the most threatening. And we make a threat map instead of a suitability map. But in any case, the client or the expert or experts decide the values for those weights. And then this is actually kind of maybe a modification of this, where you just ask them to rate, to rank, or to the order the weights, and you assign those rank orders as the weights, or the inverse of those rank orders sometimes, depending on how they rank them. If they rank them from 1 being the most important, then it would be the inverse rank order that you'd actually use for doing that. Here's an example of that. So we have, these are the different criterions that are going to get turned into basically GIS functions. Okay? These distance to nearest competitor, distance to major road, parking density, and parcel cost. So this would be something if we wanted to site a new store or a new location. What the experts in this case have determined is the parcel cost is the most important factor. Okay? The parking density is the least important factor. The distance to the major roads, and then the distance to the nearest competitor is the second most important factor. And so in this case, since they've ranked them meaning 1 is the most important, you would have to take the inverse. Okay? And it's simple in this case. You just, there's the math explaining it, but basically what you're doing is 1 is now 4, and 4 is now 1, and 3 is 2. You're just reversing the order, recounting it. And so the weights here are using a common scale. You're dividing it by 10 so that they will all add back up to 10. Okay. Why would you do that? Why would you do this math? Well, this math wouldn't necessarily be this one right here, this column. This wouldn't be as important unless you wanted to then compare it to an analysis done at a later time. Because your weights, if they all scale to the same number, will always produce values between those initial values. You're basically scaling the weights by assigning them a value on a common scale. The other thing that you have to do, besides coming up with weights, is you have to oftentimes talk to experts, and as a GIS scientist or GIS analyst, you have to talk to the experts and get them to make this step here. Sometimes they'll tell you, hey, well, when we want to create a new location for this, slopes can't be too steep. What do you mean by too steep? Well, after some discussion, you might realize that it really doesn't matter as long as the slopes are less than 30 degrees. If the slopes are less than 30 degrees, we're okay with that. It might be that they say, well, if the slope is really shallow, it doesn't cost us hardly anything, but if the slope is between 20 and 30 degrees, it'll cost us a little bit more, but over 30 we don't want it. And then that would be a different refined criteria. That would be a refined criteria that says slopes less than 30 degrees means it's going to cost this much, less than 20 means it's going to cost this much, which would be even less. Over 30 means that it's cost prohibitive. So in any case, you have all these criteria that you come up with in order to come up with a good location for whatever they're trying to plan. Southern aspects preferred, you convert that into aspects between 90 and 270. The soils have to be suitable for septic systems. That's a reclassification operation. They have to be far enough from roads to provide privacy, but not isolated. In other words, they have to be between 300 and 200 meters from the road. All right, so here is the implementation of something similar to that. So here's our refined criteria, and here is a flow chart that we're going to use to actually come up with that. It's fairly complex. I mean, it's not overly complex. There's 20 operations. In other words, there's 20 circles on this map, on this flow chart, and there's 15 layers, 15 squares. But we're actually only starting with 1, 2, 3 different layers. 3 layers to complete this task. Right? So the first thing that we want to do with that first criteria that we had there is to derive slope and aspect from elevation. See how elevation's over there. We're going to derive slope from elevation. We're going to derive aspect from elevation. And then, once we do that, we need to reclass slope and say every area that's less than 30 is okay. Every area that's not less than 30, we don't want it. So it's basically just a 0 or a 1. Okay? Anytime there's a criteria that can be boiled down into yes or no, or bad and good, 0 and 1, and usually 0 means it's unacceptable, 1 means it's acceptable. All right, aspect layer. In the aspect layer, we're going to reclassify those areas that are between 90 and 270 as southern facing, and so those are acceptable, and anything else is unacceptable. So that's the result of these. This here is the same as this part of the flow chart. So right now we're at the slope reclass layer and the aspect reclass layer. We've done that. That represents this. All right, the next thing is to combine the slope reclass layer and the aspect reclass layer. Now, this could be done in a few different ways. Notice it doesn't say here, maybe I should have, but it says overlay, right? Well, if these are both still raster data sets, we could overlay them by basically, how would you overlay them so that you would get the right, remember this is a bunch of 1s and 0s, and this is a bunch of 1s and 0s. The 0s represent areas that you don't want, the 1s represent areas you do want. If there's a 0 in either layer, it's not good. So, simple mathematical way to combine those two to make it so that there are now 0s only in the areas you want. Sorry, 1s only in the areas you want. Anybody think of the way you do that? Kind of drawn out here. What's that? You could use an and statement. So in other words, you'd say if slope suitability is 1 and the aspect suitability is 1, then you just use the word the and. So and. We say 1 and 1, we get 1. Both of these are 0, so the output's going to be 0. Only one of these is 1, so the output's 0. The other way that we could do that, if we just had a bunch of 1s and 0s, is use multiplication, right? 0 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0. Either one would work, actually. So you could use the spatial analyst tool, and you could go under the operation and put an and in the middle, or I'm using or saying, or you could just multiply the two layers, and you get the same result because it's all 1s and 0s. You get the same result as the output. All right. Now, if it was 1s and 5s or something, then you could get 5s. If you did the multiplication problem, but if you did the and or, you get 1s and 0s. So that is, the and statement, you get 1s. So that's probably the safer bet, but either one would work. I just wanted to bring that up. Okay, so now we're down to here. So we did this overlay. So the overlay is saying, what is the layers that are, what are the areas that are suitable versus not suitable? Here now, this person has chosen to do a raster to vector conversion. In other words, we're converting all these dots, these 1 and 0 dots, into vectors, into polygons. So now we have one polygon that represents the correct layers, and one polygon, the one polygon represents the suitability layer, and the zeros represent not suitable. All right, and so we're just going to reclass that, dissolve it, and come up with a suitable terrain layer. So we have one, we didn't have one polygon, we had lots of polygons. Now we have one polygon. All right. So that's all the elevation items. The next step is that we could take the soils. And the soils, we're simply trying to find the soils that are okay to put a septic tank on. So we might have to ask a scientist that studies that sort of thing, or a specialist that does that sort of thing. And basically take out all of the soils that were not suitable. And so we only have the suitable soils, and then dissolve them. So now we have a polygon that represents all suitable soils. The results here are a polygon that represents all the suitable terrain areas. So 2 polygon layers, and we can overlay those two and find the intersection of only the terrain and only the suitable soils areas. So it's suitable for each. We've overlaid it. We probably want to do a union or intersect there. That overlay, this overlay here. We want to find just the areas where they overlap. Yes. So what is that? An intersect or a union? That's right. It's an intersect. We want to intersect these two. We find just the areas where they overlap, and that's the terrain and soils. All right. And then finally, with roads, we extract the major roads because we said we want to be within 300 meters of a major road, but not more than 2 kilometers away from a major road. Or sorry, within 2 kilometers, but not more. I'm confusing myself. More than 300, but not more than 2 kilometers away from a major road. That's correct. So we buffer both of those, and we basically use the 300-meter buffer to clip out the says overlay here, but again, do you remember from a previous lab what the name of the tool is that will take and remove the 300-meter buffer from the 2-kilometer buffer? Do you remember the name of that tool? Starts with an E. ArcGIS calls it kind of like erase. Yeah, ArcGIS calls it erase. So we take our 2-kilometer buffer layer and our 300-meter buffer layer, and we erase from the 2-kilometer buffer the area that's the 3-kilometer buffer. Does that make sense? So now what we did was the 2-kilometer buffer goes out 2 kilometers from the road. We also said it was only suitable if it was more than 300 meters from the road. So we're erasing out that middle part of it. That's this flow diagram just uses the word overlay. It doesn't get at the specific overlay that's needed. And actually, ArcGIS is so widespread that you probably use ArcGIS. But if you didn't use ArcGIS, you may have to do that differently, or it may have a different name. But let's say you didn't have access to the erase tool. You could do a union, and then you could delete. You can open up the attribute table after the union and delete the area where they intersected, because that would be burned in to the new polygon. Actually, let's see if I can do that real quick, just to drive that point home here. Okay, still have last week's lab up here, so I'm going to hit new. Okay, add some data here. Add data. Okay, so here's all the interstates in the United States. So I'm going to buffer. This is different than, not the same data, obviously. I'm going to buffer, though, using the way up here, data management, or analysis. So I'm going to buffer the interstates to 20 kilometers. Okay, and then I'm going to buffer them again to 100 kilometers. Oh, I typed in 1,000 in there. Well, it still worked, but I'm going to do 100. 100 kilometers. Okay, this will look a little better. Okay, so now if I put change the layout here, put the one buffer on top of the other. What I'm trying to do here is erase this line from this so that there's a hole there, because that's also unsuitable. This is unsuitable, which is fine because we don't have anything out here. But that area right there, next to the interstate, is also unsuitable according to the criteria in our model. So I could, like I said, I can go down to overlay, erase, and put in the larger buffers and the erase feature, run those, and if I do that, I'll wind up with, when it finishes, I'll wind up with what I want, those areas erased away. So now if I delete these other layers, you can see that I've got areas I don't want. What can have access to the erase tool? That's what I was trying to get at. Was this question asked in the lab? I used to ask this in the lab. I forgot off the top of my head. I guess not. So you'll notice that the erase tool is only in the advanced. It's only in the advanced license. So if you only had regular version of ArcGIS, basic or standard, you couldn't run the erase tool. Well, what would you do? Well, it would actually be similar to something you've done in other labs. You could, first what you'd want to do is open up one of the buffers, the interstate, the smaller buffer, and create a new field, or just use any of these other fields that don't really matter. I'm going to use I'll just make a new field. I'm going to add a field. I'm going to call it in small buffer, in small buff. And I'm going to code it 1, the whole value 1. So it's got a 1 everywhere. And then what I'm going to do is do the union between the buffer and the buffer 2. And once I do that, the buffers from the first buffer will be burned in to the second buffer, the boundary. Watch what it looks like. I'm going to delete. I'm going to remove that. This one's taking a little longer to actually work here. Okay, well, I don't know why it's taking so long. Just a second. All right. Well, anyway, when it finishes, what will happen is that it will burn those new layers, the smaller buffer into the larger buffer. But only those areas will have that attribute field that I added with the 1 in it. And then we could go in the attribute table and delete those. We could do that later. We can come back to it to show you what that looks like. I don't want to wait forever. Okay, so that's right here. So this, basically what I'm trying to say is that, oh, we were past this one. Basically what I was trying to say is this overlay function right here is probably an erase if we're doing ArcGIS. Even if we weren't using ArcGIS, we could come up with a way to do that. We might have to do it in 2 steps. So once we have those overlay, we have the areas that are suitable. Okay. Now in this case, the roads layer went outside the study area. So what we'll want to do is reclip them to the study area boundary. The buffers got bigger. And So we re-clipped them, and so we have just the road buffers within this polygon. That's what that preliminary buffer is. That's the road buffer. And then we could reclass those to the suitable. And then finally, we overlay all these suitable layers using another intersect and come up with a suitable sites layer. And our attribute table may end up looking something like this. In fact, if we had done a union instead of an intersect, it would look a lot like this. So we have zeros and ones. Anywhere where it was all ones would be suitable. If we end up doing intersects, we'd only have the ones left in our file. We'd only have those areas where they were all together. All right, let's see if this is finished. Still not finished. That's going out. That's going a long time. Spawn slideshow. Now, it may be like, let's say we were doing this analysis, and these were all just factors. This table was all just factors. In that case, we would have wanted to use a union, and we would add these up and find the most suitable areas were all fours, and the least suitable areas were zeros. Is there a fire alarm down there? All right. Well, why don't we take a break right now? We'll just take everybody's break right now. We'll come back in 15 minutes. There's only one more slide here. We'll talk about it. This will be done. I'll be able to talk about that. So 15-minute break. Unless the thing keeps going on, just leave it on so I can hear that it's still happening. I'm going to turn it down a little bit here, though. So yeah, just take our 15-minute break right now. We'll come back at, actually, let's just say 2:15. So that'll be almost 20 minutes. 127? Oh, I don't have my keys today. I don't have my keys today, but I'll find somebody for you.
Mine was too, and he had to fix it for me. I don't know how to fix it.
I'll leave it sideways now, but when I tried
He'll fix it.
the coloring one, like I literally, I made the print next to 50 on the hill smear, and that's it. But I don't understand what it means. Between the leaf on the smear elevation, I can't get the coloring. I don't know any of it.
Let's see if we've got it correct. So it wants the hill smooth, hill shape one. That's the one that needs to be colored, right?
Now I made that one this one.
I mean, I did it with, I did it when the, you know, one of the same color. Because I know that Dr. I think you did do everything right. It's just now it's a matter of getting the right one. But I think what I mean by that is just make sure that the color shows that And so it's probably something really simple, but I'm having trouble on lap time too because it's not looking like something so in these pictures. So I'm gonna have to ask him what it is. But yeah, I'm not sure on just I would ask him. Do it again at insert the movement and see what they call it. Yeah, that was a relief. Yes.
I know when he's reading.
Okay, so you're using the wrong. You did something wrong here. I did the same thing and I put it back in there.
Go and open it up.
Alright, so. Is that one not working for you? Okay.
Put 'em okay, put 'em in that little like,
How do you do that? Very light right?
yeah, okay, so go to insert.
Up here?
Yeah.
That's our okay,
Yeah,
so I
and then
just
you
drag
drag
it.
it.
Okay. Cool, thanks so much.
Yeah, you just go to insert. The other side.
Okay.
There you go.
Move that mode.
Right, right. So this looks like.
Yeah.
So, like, you reversed these two. So this one should be black to white. And this one should be now they look very simple.
Does it say that specifically? I mean, I'm just trying to like, I just want to make sure that I'm not crazy. I didn't know. Yeah, so. I don't know, I guess it doesn't specifically say which one to add the color to, I just assumed that this was to add that to the hill shade.
Where does it say?
Derive the hill shade here. Oh yeah, right here it says make the hill shade semi-transparent.
Yeah, I guess it doesn't say where to make the color. It doesn't say where to make the color. You're right. But the color gets added to the symmetric thing. I mean, if you think about it, like, so what's happening is that the hillshade is colored based on how much light is coming in. So that one should be just a light to dark. How much shadow, the shadows, yeah. So making the shadows. doesn't have as much. Let me check just a second.
Why does mine look like this? I think it's pretty thing up here that has to be. Dragging what? Yes, yeah, just grab this and pull it down. Well, it's something of it. It's something to do with. Oh. No, you put one in each, like each one in that, bunch like everything in there. Oh, yeah, I think I need that. Yeah. Sorry. So you go shoot insert, and then that frame. So now you'll put that. Just leave that one there. That one there. Yeah. That one.
Yeah. Somebody else had that problem. So,
We'll have to have that whenever we make that last map. That's what you're doing right now.
we solved it by,
You made a new one and deleted that one, and it worked.
I did that too, I rewrote it 3 times. I don't know what that.
so, this is because you've got a bunch of really small rivers. And then this is the streams, right?
Yeah, I'll do that scale. Scale, but other than that.
Raster to polyline. Did you say no data? I think we changed this. Yeah, I think that's what solved the problem. That's what solved the problem. Yeah, that is what we're doing. I'll get to that in a second.
Okay.
All right. All right, so fire alarm looks like it's over. So we've got our last slide here, which I'm sure you've all read over now anyway, but basically, in order to do this cartographic modeling process, you do have to have a good idea of what you're doing, and then you have to convert that into steps, into processing steps. You do have to pay attention to the projection that your data is in, pay attention to if you have the accuracy, the the spatial and attribute data that you need, and then you need to figure out how to go through the flow of your process. In order to implement this, we're going to do a lab today, and I'm going to get a little bit further in the lab than I did in the past because, like I said, it's starting to steer a little bit more toward letting you do a lot of it on your own. So let's look at it, and if you'd like to follow along, you can. If not, then it'll be on the video. Looks like I still have more than enough room. Is this? Yeah, it's recording. Okay, great. All right, so I'm gonna first refresh ArcMap here, so I get a brand new ArcMap. Oh, actually, before I do that, this actually looks like it ran through. See how it burned those lines in? I'm gonna do an erase without doing an erase real quick. So I did the union, and I'm going to open the attribute table, and I added that new field called, where did I add it? In small buff, right here. So I'm going to sort that, and I can also do this by doing select by attributes. In fact, that might be the faster option. So let me do that. Or not. I could manipulate the table, but this looks like it's taking forever. It's still taking forever. Maybe I will. I'm just going to cancel this. Get a brand new version of ArcGIS. Actually, I'll just open up another ArcGIS so that we can go back to that one. All right, well, that's opening. I'm going to look at the lecture, the lab for today. And that's this one. And I'm going to download the data. And I've got to unzip it someplace like we've been doing with other labs. So our lab today concerns this little animal right here. It's called a ruffed grouse. We're going to find some good ruffed grouse habitat. So I'm going to place this in C. I'm going to put it in C temp just because I want to be able to get to it easy, and I want to delete it later. I don't want to have it on my hard drive forever. Yeah. I do, but I haven't uploaded in a few weeks. All right. If you read right here, this is a game where it describes a disturbed forest ecosystem. So if it's basically burned or clear cut every 40 to 50 years. If I disturbed, maybe once or twice in one person's lifetime. This product, this mosaic provides food and cover in close proximity and refuge from predators. That's what we're going to do, is to find these areas that the rough grouse like. So we have to find areas that have brushy areas and young aspen stands. Okay? Disturbed areas have more brush than old established forests. So we need to select aspen stands that are less than 19 to 34 years old. So that's one of the criteria. Another one of the criteria is mature aspen stands with an understory of hazel or ironwood to provide food in the fall. So these are areas that are older than 34 years. And then the dense sapling aspen stands provide root cover. Those are 18 years or younger, and away from areas of old tall conifers that serve as roosts for raptors. Okay? So we don't want conifer stands that are more than 105 years old. Okay. So we want areas that are near all three of these different types of areas and not near the tall conifers. So they have to meet these criteria. The buffer around each stand, and the overlaps of the buffers are the good areas, except for the tall pine ones, which are the bad areas, so those are being cut out. All right, so use the vegetation layer. Hopefully it's done downloading now. So let's add this vegetation layer so we can start doing the lab. Let's see where it is. I thought I renamed it, but I guess I didn't. It's labeled Lab 13 in the zip file, but Lab 10 outside the zip file. Just different times it's been taught, it has a different number. Sorry, that's confusing. Okay, so it should be Lab 10. So now I'm going to hit the Add Data button, and find that data, ctemp is where I put it. Lab 10, I renamed it the correct name. And I'm going to add it all because we're going to use it eventually, but the vegetation layer is what we're going to look at first. So this vegetation layer right here. So zoom down into this. The cloquet forest, that's what that cloquet prefix means. And here's the cloquet vegetation. I'm going to open up the attribute table, and there's some codes here. We've got C-type, size, density, origin, land cover. Okay. So we've got some pine stands. These are conifers, and we've got some spruce and some aspen. See the aspen there? So we can answer all of our questions. In fact, if we look back at the yeah. So here's the vegetation codes. If we look back at the lab, now it's called Lab 11 in this one. Called Lab 10, yeah. Okay. So I have it like called Lab 13, Lab 11, and Lab 10. Sorry about the inconsistency. All right, so these are the vegetation codes. The vegetation codes tell you what the C type is the species. The density is how dense it is. The seedlings, saplings, poles, and saw lumber trees are the size CL. And then we've got the origin here for the year, so we can do the age. Okay. So this tells you what we need to do here. Okay. Establishment year, origin. Assume you're doing this in the year 2006, because that's the year that this lab was created. The year the data were produced. All right, so you're going to have to identify aspen and birch. So it suggests doing this by select by attributes. That's pretty easy. So we're going to separate and export those stands into a separate shapefile. So you've done something like this before, but before you've had the exact steps to do it. But this is the way I would do something like that. So we want our aspen and birch. We could use this cover type, but it's easier to use the C type. We just have to find out which ones are aspen and birch on here. So, birch and aspen are A and B. So how could we come up in select by attributes? How could we select only the aspen and the birch? First of all, let's go to select by attributes. Select by attributes. Okay, you've seen this before. So the C type is the variable that we want. So we want them to be aspen and birch or aspen or birch. If we want all of the birch and all of the aspen. Yes, that's exactly right. We want them to be or. Okay? So we want the aspen and the birch. And maybe counterintuitively, maybe not. So we use the word or to represent that we want everything. If we use the word and, they have to meet both criteria, and it's actually impossible to meet both criteria if they're both the same field. So C type equals A and, or C type equals, it's just B, right? Right? So now if we hit this button right here, it'll show us just the selected records. So these are the aspens or the birches. And here it is on the map. All those areas, they represent the aspens and the birches. So the lab then suggests that we export this layer and call it aspen birch. So data, export data, and we're going to save that in the same directory that you've been working in. That's C temp lab 10 for me. And I'm going to call this aspen birch. Aspen birch. Export it. I want to add it to the map. So now I've got those layers added. And I think it's either this step or the next step where it actually tells you how much they should have selected. So we did this. Okay, so the next step where it tells you how much you should have selected. So then open the aspen birch table and alternatively select young, intermediate, or old tree stands, exporting each to 3 new shape files. Because we need the old, the medium, and the intermediate. The old, the intermediate, and the young as separate ones. Okay? So it's telling us right here that we should get 30 are young, less than 18 years. 25 are intermediate, and 30 are old. So we should get these results. So as we're doing it, let's make sure we can get those results. And that's why that's included there. So we'll start out with the young, since that's what the one they start out with. So they're saying we can go ahead and take their word for it. So from 1988, it seems like a long time ago, right? But that's kind of as young as the trees. 1988 to 2006. So one thing that we could just do is say greater than 1988. We don't have to do the other direction. So we could go like this. I'm going to turn off the whole vegetation layer just because I don't want it to distract what I'm doing. And I open up the aspen birch attribute table. And I'm going to select using the origin. I'm going to use select by attributes to say, okay, I want to find all of the trees where the origin is greater than 1988. Yeah. Oh, maybe it's text. So I thought I was going to be clever, but I can't. I'm not. I don't think. Yours worked? Oh, because it needs to be in quotes. Like that. Did you put it in quotes?
Yeah, that's what it was. I got these values from the origin.
Yep.
And it's just one of those.
So that'll work. You just need to have the quotes because it's text. All right. So origins greater than 1988, and that'll give you all the ones that you need to know. I think. Let's sort this and well, just hit this button. Actually, though, I'm having an issue, right? Because it said that there would be 30 records, and I got 26 records. Yep. So I guess we'll do it the way. But I don't see how. Oh, I see what's happening. I think I see what's happening. So 88, it's not going out to 2000, it looks like. 2001, 2006. See how I'm not getting any of the 2000 ones? No 2000s. And so, did the data get messed up somehow? I think that's actually the issue. There are some that are zeros. I think those are just, let's see. Let me see here real quick. Select by attributes. What happens if we say greater than or equal to? We get 30. Back through 1988, so through 1988 would be correct. Right? So that's the way it is. I think the ones that are zeros are just undetermined year. They won't be included, basically. So 30 records are young, less than 18 years old. From today's year, which is 2006, back through 1988, so inclusive of 1988. So it should be greater than or equal to. So we got 30. So let's go ahead and now export Aspen Birch. Now, by default, this is selected features. Just make sure it stays that way. So you're only exporting the selected features. So we're going to call these the youngins, the young ones, or just young. All right. So now we've those guys are purple. Those are all the young Aspen Birch stations. Move this over just a bit so it fits on the page there, as was suggested. Okay, so we can now do the same thing with 1987 through 1972. So we can select by attributes, but this time we will have to bookend it. So this one will be, what year was it going back to? 1972. And then we'll have to say origin less than or equal to, or 1987. No. And. Why is and the right answer there and not or? Yeah, if we do and, it has to meet both criteria. If we do or, it has to meet either criteria. And all the records meet either one of the other criteria, since one's saying everything lower and everything higher, and they're actually like standing on this side of the number line. So if I say I want everything to be bigger than this one or less than this one, then we get everything. Okay? But if I say and, I'm just getting the overlap in between. So messed up with the or there. All right, so we did it. We don't actually have to close that if we don't want to. We can just go over here and say File, Export Map, not Export Map. Go up to, oh, did I do this on the, no, I didn't. Good. I thought I did this on Young for a second. Okay, export data, and this one's called intermediate, or middle. I'm going to say middle because I can't spell intermediate. All right, I can spell it if I have a spell checker, but there's no spell checker. They should have spell checkers everywhere, including in file name. All right. So those are all the middle. And then finally, we're going to get the old ones. So from 1971 to 1988. So now I can just change these. 1888, thank you. So I'll change this one to 1888, and this one to 1971. And I got 30, which is what I should have. And I'll go to Aspen Birch and export. And I'll call this old. I'm gonna hurt their feelings. Old trees. They don't like to be called old. All right. So let me change the color on this one real quick to kind of like coral color. So now there are 3 different colors. I'm going to say selection, clear selection. And now we can see those 3 different colors. Green for the Aspen Birch, which in this case, these are the ones that were marked as 0. So they're of undetermined age, so we're basically throwing them out. Youngs are now the purple color. Middles are the lighter pink color, and olds are the darker pink, the coral color. All right. Yep. This is the line that tells you to do that. Okay, after creating each Aspen Birch age layer class, we're going to buffer each layer at 300 meters. Then, we're going to overlay the 3 layers using union or intersect commands to create a cover flood layer. Okay? In this case, like I kind of started in the lecture, in this case I think intersect is perhaps the easiest for combining them because what you're trying to say is they have to meet all 3 criteria in order to be okay. If the model was, it'd be best if they met all 3, but it's still okay if they only meet 2. There's probably some rough grouse in those areas. Then we want to do union. Okay? But we're not. We're just saying yes or no. It's either acceptable or unacceptable. In those cases, it'd be good to combine them. So you can do that. That's pretty easy. It's just intersect. Now, the lab suggests that you do these in a serial manner so you kind of see the result. But you don't, I guess you don't have to. You can throw three layers into one intersect. And what's the property of math? Like where A plus B is the same as B plus A, or A plus B plus C is the same as C plus B plus A. What's that called? Anyway. What's that? Yeah. So the order of operations matters for some spatial operations, but for intersect, the order of operations actually doesn't matter. Okay? It's like multiplication, actually. It's like more like multiplication than it is like addition. But still, in multiplication, order of operations doesn't matter either. If we're all multiplying everything, it doesn't matter. Now, if you're doing union operations, order of operation does matter. But unioning all 3 of them has the same effect as unioning 1 at a time. But if you were to union 2 and intersect 1, that'd be different than unioning the other 2 and intersecting. Okay. But anyway, it tells you to do it in a serial manner. It technically, if you're going to do the intersect route, you don't have to. All right. Now, finally, you'll need to subtract the areas in cover food that are also near older conifers. Okay? So, the first thing you need to do is to find the older conifer areas. Then, after you find the older conifer areas, you need to run an overlay. What overlay function that we already talked about in today's lab would you want to use? Erase. Yes, erase is the best one to use in this case. If you didn't have access to erase, you could do it the way that I was working on over here, which might finally be done. And that is to go into here and say select by attributes and say in small buff. Where'd it go? In small buff is equal to 0. And then export just those 0 values. But we do have access to erase, so you can do that. All right, so we already did this part. We haven't yet buffered them or intersected them, but we did talk about those things. And so you need to go back to the original data set, and this time you're going to select any conifer. White pine, red pine, jack pine, Scotch pine, or white spruce. So you're going to have a big old OR statement. And these are ORs because it can be any of those types. Then save that as a layer and find only those that are older than 1900. So it's greater than 0, just so that 0 won't be included, and less than 1900, 1901. So you get that layer, and then you buffer that 50 meters, and then subtract or erase that from the other layer that you create. All right? And then once you do that, you're all set. Okay, going to include the other things here. Anybody have any questions? Now, the first part of next week's lab is to actually draw a diagram of what you did. You draw a flow chart of what you did. So, just a heads up. The first part of next week's lab, you're basically taking this lab 10 and just making a flow chart where the circles represent the layers. So your circle, the squares represent the layers. So you have a square saying the vegetation layer, well, that's really the only one you start with, and then everything comes out from that, the vegetation. The other layers are just cartographic. Okay. All right. So let's go ahead and. Are there any questions on this lab? Anybody from the on the codes? Go ahead and work on this lab or previous labs. I'll answer your questions. You all had some questions. You guys, somebody back there had some questions before. No? I thought somebody had their hand up when I went back to this lab. Okay.
I have a lecture-related question.
Sure.
We have a lot of time for like a review.
Yes. So the question is there a review? And the answer is yes. That's why there's no lab on the last day of class. So the lab time will be the review for the final. Yep. Sorry, I was going to put that, but I forgot to say it. You have a question? Yeah, I'll think about that. You have a question? Yes, I need to do that.
For various reasons.
Okay, so yeah, it'd be helpful to like have people identify which computers don't work. But is it pretty much all the computers now based in that?
Basically all of them that no one's sitting at but that one.
Now, what's the symptom? Is it always the same, or just they don't even turn on?
This one doesn't turn on.
That
That one's
one's
not
not
connected to
Internet?
the network. That one in the VGA cable's on. That one's not connected to the VGA. It's not a channel. It's not that.
Okay. All right. Yeah, it seems like we have a lot of work to do to make the computers work. Anybody down there? Corey, down there yet? Okay. I'm gonna go.